Hello, hello, hello. Hello, can you hear me?
Yes, sir.
Okay, so we'll wait a few more for the others to come. Okay, Okay, so I'll start. Um, so, hi Divya, can you hear me properly?
Yes, sir, I can hear.
Okay, so as you can see, my name is Sahil. I am from IIT Hyderabad. I am a PhD student in physics department. I work in um, biophysics modeling, mathematical modeling of biological systems in those kind of areas. So I'll be doing your TA. So can you introduce yourself first? Like where are you from? What do you study? So that I can get an idea like what's your background. So that will help me explain stuff.
Sir, I'm Mary Varghese. I'm second year MSc student in Central University of Karnataka in physics.
Okay.
Mm, I'd love to pursue biophysics as my in my future studies.
Okay, you are a physics student. Okay, that's great. So right, only you are here. So okay, fine. Like, do you have you gone through the video lectures by Professor Chaitanya?
Sir, I couldn't hear you for a few minutes. My
Okay,
phone
so
was.
I'll give you a heads up. So there is this uh, right now in my campus there is a power cut. Okay, so I am doing this with my uh, mobile internet. So there can be a lag or some kind of issue till the power comes back. So apologies for that. So I am saying that
Uh,
yes.
no, sir, it was my mistake. Like a call came. So.
Okay, yeah, that's fine. Still, this is a problem. Like there could be a lag with, like sometimes like I might be writing, and you might not see it instantly. There could be a time mismatch in my writing and the whatever you are seeing. Anyway, what were you asking? So, have you gone through the lectures?
I completed until Navier toxification. I have few more to watch.
Uh, till Navier Stokes equation, like week one. Week one does not
Week
cover
two, in week
week two. Yeah, so what happened is
mm.
last Saturday also same thing happened. I couldn't take. So do you know that it will be an extra class on this? I guess Tuesday.
Last Saturday there was a link, but I couldn't attend. I sent a mail, but no one responded.
Yes. So I'll tell you what. Uh, so the thing is, last Saturday also there was a technical issue here from my side only. So I couldn't take this. It will be, so we are lagging behind one class, so that will be on
Okay.
August 6th.
Okay.
August 6th, 2024, 3 p.m. to 5 p.m. Okay,
Mm.
so I'll start with the first week. So my job here is to, so is there any assignments given?
Uh, Week one there was an assignment. Week Every week there will be an assignment. So week one I have completed.
Week one, there is an assignment in the class, right? Okay.
Yeah.
Okay, so see, so what I'll do here is I wouldn't like I will try to have a discussion about whatever is going, whatever is there, any doubts, or if there is nothing, I can tell you something from my side about that course. So today, what I'll do is I'll go through week one because this is the first class, and first class I was planning to have week one stuff discussed. Okay. So have you solved the assignments of week one?
Yeah. I tried to solve. Yeah. I
Okay.
completed. I submitted, but they allow resubmission also if there is any clarification.
Okay. So was there any difficulties going through?
A few questions. I forgot. I have to check again.
Okay, so
I'm
one.
currently going to week two.
Okay, so one thing I will tell you, if you have any doubts regarding the topic, mm, if you have doubts regarding technicalities like what to submit assignments and all, you write to the person from NPTEL. And if you have doubts or any queries about or any questions that you can want to discuss, you can write in the discussion forum, or better it will be you, if you can mail me directly here. Okay, here in this email you can directly write it to me. Okay.
Okay, sir.
Okay, so you have like right now you have assignments, two assignments in your hand, right? Week 1 and week 2.
Yeah, week one I completed,
And
but
week 2 you haven't.
week two I
So
haven't.
can you do me a favor? So can you send me week 2 about the assignments? Like
It will
assignment means
take
not the
time. Should
solution,
I
but
mail you
yeah, the questions. Okay.
questions? How will I download that? I'll screenshot you and just attach to your mail. That's it. That's enough.
Fine, you can do that. Anywhere, like any whatever you feel like. Okay, that will be great. Like I don't have that questions, um, so if I have it, I can discuss similar questions next week. Next week means Tuesday.
Okay. Week one only, right? Or
No,
both?
week 2, week 1 today I will not discuss any assignment. I guess week 1 assignment should not be a problem for you, right?
Most of them were like questions. Since I have more of a physics background, some
Mm-hmm.
questions were I couldn't understand. Like it was more of biological aspects.
Okay, can you
And stuff like
tell some of it?
uh, the length of E. coli and human genomes. That will be like a plus two knowledge.
Mm-hmm.
Uh, but how many membrane bilayers? There was a question. How many membrane bilayers will be an imaginary line drawn from a fibroblast to the longest axis of cell passing through its geometric center?
Okay, I missed it. Can you repeat?
Mhm.
How many?
Minimally,
How
membrane bilayers,
membrane
bilayers
bilayers
will an imaginary line,
will an
imaginary
imaginary
line
lines
drawn from a fibroblast
from a fibroblast
to the longest axis of the cell,
longest
axis of the cell,
of the cell
and passing through its geometric center.
and
Passing through its geometric center.
okay, and the answer is 2 or something.
Yes, sir. When I checked, it was two.
Okay,
Can you explain?
I think I haven't seen this kind of question ever, so I'll try to answer. Let's say this is a cell. Okay, so now imaginary line drawn. So can you see the screen, right? The writing.
Yes, sir, I can see.
Okay, so how many membrane bilayers with an imaginary line drawn from a imaginary line drawn from a fibroblast to the longest axis? Let's say this is the longest axis. I think it is because of this exact position of this fibroblast. uh, it stays at the poles. That is why you can have only two like this. Okay, so okay, I will have to check.
Bilayer, two layers should be there. So when an axis crossing four intersections will be there.
Yes, yes, come again. Hello.
It said like it's given membrane bilayer.
Hmm.
Bilayer means two
But
layers will be there. No?
no,
So
bilayer means membrane always have a bilayer like this. Couldn't hear you. Hello.
Here you have drawn only one a cell as a cell membrane. Here it is given bilayer. So two layers will be there.
Let's say okay, the cells have bilayer like this. Okay. And then what did you say? Hello.
Sir, I am also going through the question again. So,
Oh, you're going to the question.
yeah.
Okay, okay. Okay, see, I can't give you an explanation right now. I'll check properly and give you proper explanation. Okay. Hello.
Okay,
Sorry for that. Do one thing. Send me both of the
sir.
assignments. Okay. And in the next class, I'll try to give this answer. And I don't solve week two. Like I don't give you the solution of the week two. But what I'll do, I'll give you hints and all uh, regarding these questions. Okay. Will that be fine?
Okay, sir.
Okay.
Yeah.
Okay. And anything else, if you want, just mail me. That will be great.
Okay.
So hold on. There has been something. I got disconnected from the. Hmm. So whatever I prepared for today, I think you will know most of them. So I have you gone through those part where he discusses about viscosity, elasticity, and all.
Yes, sir.
Okay, so just since you are a physics student, this will be very easy for you. Uh, Tell me what is viscosity. So I assume there will be there
It's a
like
simple
usually.
flow.
See, I'll tell you what happened. I assume there will be biology students and different kinds of students. Usually NPTEL courses have variety of different students. Last time I took one course of mathematical modeling. There was like different. So I tried to make it diverse. That's why some questions may be very trivial for you. Okay, but since you are the only person joined, we both can go through this. Okay.
Okay.
So tell me what is viscosity.
Uh, it's a resistance to flow.
Okay. Resistance to flow. Flow of Law of what?
Fluid, fluids, liquids.
Liquids or fluids. So any definition, like any mathematics? Let's revise viscosity together, okay?
Viscous force is given by 6 pi eta V. Sorry, it is the coefficient of viscosity.
Again,
R
come
is the
again.
radius of the object, and rho is the
This one. And are you saying this one?
the chalk drag equation.
Which one are you saying? Newton's law?
No, Stokes equation.
Stokes equation. This is the Stokes equation, right? This is Stokes equation.
Yeah.
Okay. Do you know? We'll come to this. Do you know Newton's law of viscosity?
Force is equal to that viscosity of fluid into area into rate of shear deformation.
You're saying rate of shear deformation.
Into area.
So Newton's law of viscosity. I'll tell you what was his law. He said if there is a fluid moving, and if there is a gradient of velocity. This is gradient of velocity, right? If there is a gradient in velocity in the fluid, then this force, frictional force, felt by two layers of a fluid is proportional to each other, and the proportionality constant is eta, right? Or um, am I saying correctly, Divya?
Sir, I couldn't hear you properly. Hmm.
So okay, just point me out. So so what I said, the force is proportional to gradient of velocity. If there is a fluid is moving and there is a velocity gradient of this fluid, then there will be the each layer of the fluid is feeling a force which is proportional to the gradient of velocity. Is it correct definition? Did you hear me this time or not?
Now I can see it. Now I can hear.
Did you hear what I said? Is this definition correct or not? That was what I'm asking.
It is.
There is an area here, right? Now it is correct. Okay. So force per unit area, what is it called?
Pressure.
Pressure. Also, it is called stress, right? So, do you know this definition? Stress is proportional to strain rate. Have you come across this definition?
Yeah.
Yes. So what is the proportionality constant? What is the proportionality constant here?
Eta.
Eta. This is the viscosity, right? So this, I think in the main lectures also he has described, right? Stress is proportional to strain rate. So this happens with fluid and viscous fluids. And now let's revise what there is this ball drop experiment. Remember?
Yeah.
So let's say ball has mass m, it is feeling gravitational force g, buoyant force fb, and frictional force fd. So do you know the values of frictional force?
That is 6 by eta. The drag force is 6 by eta. With
rv.
Stokes by Stokes equation.
Yes, and buoyant force.
And gravitation.
Okay,
Buoyant force is mass into rho into v into g. Rho is
rho v, sorry, volume g, volume displaced, right?
displaced and density of fluid into volume displaced into
And this is mg.
expression utilized.
Yes. So this is correct. And what is volume displaced? Is equals.
It's same as the
Uh-huh.
volume of object. It's same as the volume of object.
Yes. These are pretty easy for you because you are a physicist. So this is Archimedes principle, right? Something. So can you tell me why the terminal velocity is reached?
When both forces become equal.
Yes. So why doesn't it stop?
When the gravitational
Will it stop?
it attains a constant velocity and it moves down.
Let's say you have an infinitely long mm, this thing like this. So will the ball stop falling if the forces are balanced?
Velocity, that is terminal velocity. It won't accelerate
It won't
after a
accelerate.
point.
It won't accelerate. It will just have terminal velocity and go like this. Correct. And now tell me what is elasticity.
Elasticity, like stress is directly proportional to strain rate. In that case, stress is directly proportional to strain.
Strain, not strain rate, right? What is the constant? Some E, right? This is Young's modulus or elastic constant. This you know. So I won't go into details of this. Now tell me what is viscoelasticity. This we may discuss today if you want. So what is
Viscoelastic material means they are both fluid and solid at the same time.
What do you mean by fluid and solid?
It has both properties of fluid and solid.
Okay, give me an example.
Like some Newtonian fluids will be like cornstarch.
Hold on. Newtonian fluid. Now, what is a Newtonian fluid?
I'm not.
No, I'm
Uh,
not. I'm not testing you. First of all, we are just having a discussion.
I'm,
Yeah.
I'm sure I'm just,
Well,
it can't,
let's go slow and like we'll have understanding about this. Okay. So, what is Newtonian fluid? So, just whatever terms comes to your mind, throw it out. I'll write it down and we'll have a discussion about it. Okay. So you said both fluid. So one thing you said both fluid and solid behavior. Okay. Both fluid and solid behavior. Now one thing, another thing you said Newtonian fluid. So can you tell me what is a Newtonian fluid?
sorry, Newtonian fluid means the viscosity is not affected by
By
shear.
shear rate. Okay. So you are saying in Newtonian fluid viscosity is not affected by shear rate. So the first thing you have to know that or understand is why it is they are called Newtonian. Because of this.
Viscoelastic fluid is not Newtonian. Sorry, I have to correct myself.
No,
Viscoelastic fluid materials is non-Newtonian in nature.
yes. Why they are non-Newtonian?
It has both viscous and elastic properties. So,
Okay, so first of all, yeah, you are right. But why non-Newtonian? Because this formula you have written, this is another name is Newton's law of viscosity. Like essentially, this is not. This is actually Newton's law, where Newton whatever Newton has said. Now, if you look carefully in this equation, what is written there? F by A equals eta dv dz, right? With me, Divya?
yes, sir.
So just a naive derivation I'm trying to do. Since you are a physicist, you will know this. Eta dx dz ddt. You understood what I did?
Partial derivative with respect and second order derivative.
So
D.
what I wrote it v as as dx dt. Okay, from here. So our z axis used to be this one and this one is the x axis. Okay, so fluid is moving like this. So I wrote dv dz at dz of dx dt. Is it fine? Now rest is I'm just switched d dt dx dz. Now if you look at dx dz term, you see this is change in displacement with respect to change in distance in z direction, which is nothing but the strain, right? What is shear strain? Are you following?
Yes, sir.
Okay, so just keep responding, otherwise I think I'll think that you are not following or okay.
Shear strain, deformation.
Strain deformation, amount of deformation, yes, the epsilon. And you eventually get back this equation, right? So yes, sorry, these are the only equals, yes. So whatever follows this equation, whatever fluid is called Newtonian fluid. Fine. Fine, right?
Yes, sir.
So sigma is 7 dot. Now you, whichever liquid does not follow this, does not follow follow this relationship is non-Newtonian fluid. Now if you tell me what will be this graph for a Newtonian fluid. This graph for a Newtonian fluid.
Uh, it will be non-linear.
Newtonian.
As Newton, as n increases, eta will increase. Eta dot increases.
So this, right, sigma is equals eta epsilon dot, right? That was Newton's law. Newtonian fluid follows this.
Eta or sigma in the y-axis.
Y-axis is sigma. Stress versus strain we are trying to plot, not viscosity. We'll come to viscosity also. Now can you tell me what will be for non-Newtonian fluid, this relationship? So what do you
Can be
mean?
inverted first.
Yes.
It can be, the equation will not obey.
So this equation will
Won't
not
be
be valid
conditional.
here, right? And give me something equals what, with like what function of, let's say some function of epsilon dot. What function can be here that is not this? Just anything you can say. What is the key point here? Sigma is proportional to
It is
epsilon dot.
directly proportional.
Directly proportional to, exactly. Now
It should be. It can be.
it can
It
be,
can be inversely proportional. Inversely proportional.
or it can have, so this actually means -1, right?
It shouldn't be a function of. Your question is, it shouldn't be a function of epsilon dot.
Shouldn't be. No, it can be or cannot, maybe not.
Uh,
Okay, so I can say this, there is an n, right? Can I write it like this, like for n, for a general
yes,
case?
but it
General.
shouldn't be one. It is one.
So if n equals 1, this is Newtonian. So n can be less than 1, n can be greater than 1, right? So for n greater than 1, how it will look? This, right?
Yes.
And for n less than 1, it looks like this. Now looking at these graphs, let's say for the first graph, now I will try to have you test it, like it's your test of physical intuition. Okay, are you ready, Divya? Hello, Divya?
Hello, sir. Tell me.
Okay. No, it's don't get, are you getting nervous? Tell me first of all.
No, no, no. My
Why are you not responding? Like, are you afraid?
no, no, my headset got disrupted. So
You got
you
disrupted.
continue.
Okay. So what I'm saying, I'm gonna test your physical intuition. Since you are a physicist, how good your physics is. Your mathematics is fine. I have just seen it. Now, how from a given graph, how are you going to interpret the real physical system? That is your next test here. Now you tell me about this yellow highlighted curve. What can you tell me? Let's say I'm saying I have a material A. I have tested like stress and strain rate. Like I have done some experiment on it. I have got some value, like I have given some epsilon dot. I have calculated the sigma, and it follows this graph. Now you tell me, what can you tell about this material?
Yes, a slight change in epsilon can cause a big change in epsilon dot can cause a big
Fine.
change in sigma. So,
Yes. So let's look at part by part. Okay. Let's say this region, this region.
mm. Up to that region, it will be linear,
It's kind
same
of
as
linear.
Newtonian.
It's yeah, more or less Newtonian. So what is happening here is, with the higher value of epsilon, can I say this? You tell me correct or wrong. So for a higher value of epsilon dot, its stress increases.
It's stress increases. Okay.
Stress increases very rapidly, right?
Yes.
Now tell me, what is this stress physically, and what is this
It's a
epsilon dot?
deform. It's a pressure, like force per unit area. Maybe it may be deformed very.
Okay, first of all, pressure and force by nature, they are mathematical definitions. I'm asking some physical intuition here. So what is stress? Stress is resistance to deformation, right? Am I right or
Yes.
wrong?
Resistance. Yeah.
So if you want to deform something, how strongly it is resisting its deformation tells you how higher value of stress it has. Correct?
Can you repeat again?
So let's say you are trying to deform something. Okay. Now,
Mm.
which one will have a higher value of stress? Let's say an iron block, or let's say some what is
Got.
yeah, cotton or something. So which one will be higher value?
Iron.
Yes,
The more which is resistant has the more stress.
yes. So exactly. So stress tells you that. So higher stress means, so this region, you see this region, or the more you go here, it goes like this. Okay. And what is this
Mm.
epsilon dot is saying you? What is strain rate tells you?
Right.
Yeah, what is strain rate? Like, what is physically?
Deformation. Like, deformation. Change per change by length. Change by length. Original length.
That
Change
is
of length. Change in length by or
original.
volume. Epsilon is epsilon is delta L by L.
Epsilon is delta L
With
by
res-
L. So this is the
and
change in
then
length
strain rate will be epsilon per unit time.
per unit time. So,
Epsilon is
so can I say
right.
this? It is the how fast I am deforming. It is a measurement of that.
Epsilon dot. Sorry, the questions?
Yes, can I say epsilon dot
Mm.
is the
Um,
measurement of how fast I am deforming?
yeah.
Agreed? Like,
But how fast?
so this is the deformation. Now, epsilon, if epsilon dot is high, that is higher strain rate, that means this delta L and L is changing very fast.
Yes. Yes.
So that is how fast I am deforming a system,
Mm.
right?
Mm.
If you have doubt, just ask me, then I'll try to explain again.
So the first system that you have marked in yellow, it deforms very rapidly after a point of time.
No,
That's
no, we'll come here. We'll come here. Just tell me, strain rate
mm.
definition is clear or not?
Yes, sir.
Yes. Okay. So let me. So epsilon dot is how fast I am deforming the system, and is resistance to deformation. Do you agree on this one, these two right now?
Yes, sir. Yes, sir.
Now let's look at this Newtonian behavior first. So Newtonian behavior tells us, doesn't matter if you do it slowly or very fast, the amount of stress or amount of deformation that your fluid is going to give you will be linearly increasing. Like the more strain rate, the faster you deform it, it will have a faster value. If you slower deform it, the stress will be slower. And this nature of this graph, the response to your strain rate is not changing for Newtonian fluid. Is it correct?
Yes, sir.
Yes. Now this one tells you, like if you slowly the rate, if your rate of deformation is slow, this sigma, this kind of fluid shows a Newtonian fluid like behavior, right? But if you have a very high rate of deformation, it shows very high stress, very high resistance. That means if you are trying to deform it very quickly, it is resisting you, it wouldn't let you deform it. But if you are do it very slowly, it will have, if you, it will let you deform it. Am I correct in that sense?
Yes, sir.
Okay. So have you seen any of this, any material that behaves like this in your real life?
Soft materials.
Soft materials.
Soft.
Okay. No, that is specific example. So have you gone through the video lectures?
Yeah.
So was there any video shown on cornstarch?
Yeah, cornstarch with the ratio of 2:1 with water. Like they behave as a non-Newtonian fluid.
Yes, non-Newtonian fluid. But do you remember what exactly the video was? The experiment in MIT.
Yeah. When you like, tap it very hardly, it behaves as a solid. But when you touch it very slowly, it's more of a fluid
Exactly.
nature.
So does it match our description of this graph?
Yes, sir.
So
Exactly.
so like if you try to hit it, punch it, or very quickly remove the spoon, do you want me to play the video or do you remember it?
Yeah, I remember.
Okay, fine. So if you punch it, it's behave like solids, but if you just pour your hand inside it slowly, it behaves like a fluid. Remember?
Yeah.
So this is called shear thickening. So if you shear hard, it thickens, it solidifies. Fine.
Yes, sir.
So next up is this one. What about this? Now based on this whatever we had discussion, tell me about this one.
There will be shear thinning then.
Definitely, you are correct. Shear thinning. So what happens is, if you try to deform it very fast, it it is more fluidic than any Newtonian fluid. See, oh shit, power cut again.
Sir, your video was stuck in between.
Yes, yes, power cut. Now, now I'm back, right? You can hear me, right?
Yeah, now I can hear.
Okay, hold on. Let me join from. Oh, come on. So where were I? It's fine. Everything. Can you see the screen?
Sheer thin.
Yeah, share thinning. You can see the screen again or not?
Screen I can't see.
Okay. So screen means that thing, that whole thing I was writing on.
It's visible now.
Is it? Hold on. I can't see.
Now it went.
Uh,
Can you
hold
put
on.
it again?
Hold on. It's a lag. So, did you take biophysics as your project or what? Divya?
My project will be on fourth semester.
Oh,
I'm
you're on
applying currently.
first semester.
No,
You're
no,
on,
no. I have to do project in biophysics, so
you have to do
I'm
means
doing the course.
like what do you
My
mean?
interest is in biophysics, so
So you want to, right?
I want.
Okay. Okay. You said Central University of Karnataka. Hmm. I see.
Yes, sir.
Okay. So before that also you studied there or somewhere else? You are from which state, by the way?
Kerala. Kerala.
Kerala. I see. Okay.
My BSc I did in Kerala itself,
Kerala
in
where?
State University.
State University. Okay. One more thing I'll ask. What is your interest? Like, um, theory or experiment? Like, let's say you are doing project in biophysics,
Experimental,
or you're going to do experiments.
experimental theory, uh, like
I see.
experimental works I'm interested in. Other than theory, not theory, I'm not much interested.
Okay.
Theoretically.
Okay. Fine. Very good. So shear thinning. So what is it? How will it behave? So if you try to deform it very fast, it will behave more fluidic, like than a Newtonian fluid. Correct? So it will resist less if you try to shear it.
Yes, sir.
So any example?
More harder substances like
Harder substances like
yeah,
very
steel or iron. No, that one.
steel or iron. Like if you try to deform it very fast, does it behave like a more fluidic?
No, it won't. It won't.
Hmm.
I don't know, sir.
So the very simple one example is toothpaste.
I,
So what happens to toothpaste? Like let's say you open the toothpaste lid, and if you rotate it, will it fall away from the toothpaste? Hmm? Toothpaste tube. Let's say you have a tube. Come on. very really sorry. No, it's been
It's
like
fine.
too many power cuts and there. I don't like it. This now I can't join from that thing. So, what I was saying about toothpaste, right?
Yes, sir. Surely.
Yeah. So let's say you open the cap of the toothpaste, like toothpaste is in the tube. Now you just rotate it. Okay. So does it fall from the tube? Will it?
Come again?
Uh, you have a toothpaste, right? Toothpaste in a tube, let's say. Okay, let's say this thing. Okay, this is this is sunscreen. Okay,
Okay.
so right now this is what I have. So let's say I opened it. Does anything come out?
Mm. No.
So what if I had water
Unless
in
you
it?
it comes out.
Well, it comes out. So water is more Newtonian. Unless I press it, it wouldn't, right? So what
Mm.
am I doing by pressing it? When I am pressing it, I am
Okay.
applying shear at a rate which is faster than the natural shear rate that was given by the gravity for, at the beginning. Correct? So what happens
Yes,
is
sir.
the moment I shear it, it becomes thinner than the previous one without any shear, and that is what the behavior is, shear thinning. So this kind of material you will see a lot in your daily life. Okay.
Okay.
Okay, now I have to really join from this thing, otherwise I wanted to show you some example. What the hell? I don't know what's happening. So I can join it from my laptop, but I can't join from my iPad. The internet is connected. Give me a minute, okay?
Okay, sir.
So there is an example he did, viscoelasticity of no, viscosity of honey he calculated, right? Remember?
Yes.
And he was trying to hint towards this viscoelasticity of a cytoplasm. Now it is there. Admit. You can see this, right?
Yeah. Yes. Yes, sir.
Okay. So what is now next? I would wanted to give about a hint towards this blood. So blood is also a viscoelastic material, you know. So what happens is blood has RBCs. Okay. So this RBCs has RBC, you know, right? Hmm?
Yes, sir.
So RBCs are finite size cells. So what happens is, because of this RBCs have a finite compressibility. So this gives rise to elastic nature of blood. And there is plasma which gives viscous nature of blood. So RBCs give elastic nature and plasma gives viscous nature. So both combined, blood becomes a viscoelastic material. So if you are interested, you can go through this paper where they are saying measurement of rheologic properties of blood by a falling ball blood viscometer. So same thing they did is they did a blood calculated viscosity of blood. There is another paper I would like to, if you are interested. Are you interested?
Yes, sir.
So there is another uh, good paper if you want to go through. Like, you might not understand everything at first go, since you are an MSc first year student, but still I would like you to, if like, these are very interesting example of where exactly these biological systems and physical system gets merged. So see, let's say this one I'll just quickly give you an overview. So you see, this is the experimental setup. Here, this is the ball. Okay, the ball, like this is the tube, and this is the ball. Fine. Now here you fill it up with any liquid you want to measure the viscosity about. Now let's say you put blood in it. Okay,
Okay, sir.
and this part is filled with water. So why this water? So blood viscosity can have effect of temperature in it. So to keep it at a temperature inside the body that has, which is around 37 degrees centigrade, this water has been uh, this chamber is full of water of 37 degrees Celsius, so that this blood stays at more or less 37 degree Celsius. So this kind of an experiment is called in vitro, not exactly in vitro, which is outside the uh, actual environment of the system. Right, blood doesn't stay in this kind of jar. You take someone's blood and put it inside. Fine. Now tell me, to measure the viscosity of this blood, what are the necessary measurements you need to do?
Uh, we need to measure the radius of the ball.
Radius of the ball. Let's say since you are the one owning the ball, you know it, right? What else?
Terminal velocity.
Terminal velocity. Yes.
Then
So there is this 2 by 9. What is the do you remember the formula? 2 by 9
2
something
by
something.
9 into change in density delta rho gr square by v term. Delta rho gr square by
Let's say
v
delta rho.
terminal.
Delta rho. Do we know delta rho? We know the density of blood. We don't know the density of
Density of object means density of the fluid.
fluid. Also we can calculate density from the mass by volume concept, right? How much you have taken and how much volume you have, are you know v term. So for calculating v term, let's say I ask you to do the terminal velocity calculation. Like, what will you do? Like, I have given you this setup, what will you do? How to calculate terminal velocity?
6 with the help of the Stokes equation.
Okay, so you said uh, this equation.
But we need to know the coefficient of viscosity. Eta viscosity we need to know.
So we are
Eta.
trying to calculate
V
viscosity,
terminal
right?
is equal to.
We were trying to calculate viscosity.
No, I'm trying to find the terminal velocity.
Yes, but you don't know the viscosity. You are doing it the experiment for the first time. Let's say no one in this world have ever done this.
Wait, this.
Okay, so you're the first one. So you have to use your brain how to calculate in this experimental setup. It's easy. Just think how to measure something's velocity.
Distance by speed.
Distance by what?
Time.
Okay, distance by
Sorry.
time.
Little sir.
No, no, it's fine. Distance by time. So let's say it is going like this. Okay, sorry, it's going like this. Now you stand there in the laboratory. You mark a line here. You mark a line here. Okay, you mark a line here, line here. So the moment ball reaches here, you turn on this stopwatch. The moment the ball reaches here, you turn off the stopwatch, and you know this is, let's say, 1 centimeter. You know the velocity, right or wrong?
Yes, sir.
This is an way, right? The legit way. Okay, someone has joined now.
Sorry.
Someone is joining now. Okay. Hi, Kanumuri Anand Verma. Hello. Hello. Can you hear me? Okay. Anyway, if you can hear me, please respond with unmuting or writing in the chat. Um, so it is almost middle of the class. There is nothing much more left. So what I was saying, so the method you suggested is quite good method, but these guys, these experimentalists, what they did, they wanted to be more precise about it. So what happened in this method, you can be wrong. Like let's say you are late pressing the um, stopwatch, blah blah blah, anything can happen. So there is this interesting technique they use ultrasound probe. So what happens is this keeps sending ultrasound this way. Ultrasound, you know what is ultrasound? Divya or um, Kanamuri Anand? Hello, am I?
Yeah.
Okay, you are still here. Okay, okay, this. Hello. So if it was having problem, you can write in the chat also. In the So Divya, answer. What you know ultrasound?
Ultrasound use sound waves to
Yes, yes. So it
scan, like in scanning it means ultrasound to scan the images.
exactly. So it happens. What it happens is you send an ultrasound, and it has a reflecting point here at the ball. Now it reflects and you detect and this amplitude in this oscilloscope. So there will be peaks in this oscilloscope. Now the moment you hit this one, you get a peak. The moment it hits it again, you get another peak like this. So that's how you can get the velocity. Now let's say how are you making sure it is reaching a terminal velocity. So let's say at the beginning it will have a,
The first method you suggested, sir, can I ask a doubt?
yes.
The first method you suggested, how will it be correct? Like you suggested 2 points will mark and you'll find the distance and the time in between.
Yes, yes,
By that way, we can calculate terminal velocity. But for, when you put the ball, first it will be accelerating and it will reach the terminal velocity.
exactly.
So
That was why
we
what
don't
I,
know.
yeah. Yes, exactly that. So I'll tell you what. Say, I remember in my BSc or something, we did this viscometer experiment, not with blood, definitely, with some other viscosity. So what happens there is we have a really long tube filled with that uh, liquid, and there are markers everywhere like this. Okay. Now let's say now you do the stopwatch at every marker. and you calculate velocity at every point. Now you plot it, velocity with, let's say, 1 2 3 these marker points. Now at the initial it will have a very high velocity, next it reduces, and this will be the plot. It's like this. So now you know
Okay,
this is
sir.
the terminal velocity. Okay.
Okay, sir. But here it won't
So here also this kind of
use.
graph you can produce, but it will be more accurate. There will not be any human error first of all, and it's more accurate in a lot of senses. Okay, so I was just trying to uh, that question, like pretty sure in a serious lab no one would do this experiment like this. Okay, so it was an BSc experiment in our university where I studied. We used to did like this, but in a real experimental research work setup no one will do it like this. Everyone will do it something clever like this. Okay, fine.
Yes, sir.
So you know this viscous velocity also. Now you can calculate this raw blood. So this is what they have done it. If you are interested, you can go through this paper. I will this PDF will be uploaded in that thing, Google Meet. Okay, not Google Meet. What do you call Google Drive? The other person, can you introduce yourself? If you're not okay, I'll tell you one thing. Like next Tuesday will be extra class for the last week. Tuesday 3 to 5, and that day I'll try to solve some problems that has like is related to your assignments. Okay, so just if you can hear me, I don't know if you're not responding. Anyway, so the last thing I'll cover here, Divya, and till this point things are clear, or did you get any
Yes, sir.
clarity about stuff? So last thing about this, one thing I wanted to ask discuss, how do you measure both elastic and viscous properties? Like let's say viscous properties we can measure from here also. Now elastic property also we want to measure. So, and do you know anything about storage and loss modulus?
No, sir.
No, right? So storage and loss modulus is the measurement of viscoelasticity, G prime and G double prime. That is shear storage and loss. Okay, I'll tell you what exactly here we do to calculate. Like this is done in both experiment and in theory also, in simulation also. So hang on, listen. So let's revisit the concept of elasticity and viscosity one more time. Okay, so what elasticity tells you about how solid the system is, right? And what viscosity tells you how fluid the system is, right?
Yes, sir.
Yes. Now if I ask, like both of these concepts comes at the very basic level. The first question we ask, that what is the deformation, right? So whatever we have discussed here, do you remember this elasticity experiment? There is a rod, you put on some kg, okay, and measure this delta L, and without the rod what will be the L? This is delta L, so you calculate Young's modulus from this, right? Remember this thing, experiment in your BSc or somewhere, or do I tell?
Young's modulus experiment was there in
Yes,
our BSc.
Young's modulus experiment. So what we did there, we add some weight and measure the displacement or the deformation, right?
Yes,
Right,
sir.
yes. So you see one common thing about both of these, that be it elasticity, be it viscosity, we ask one very fundamental question about the material. That question is how the material responds in presence of deformation. Do you agree with this?
Yes.
Yes, like yes, yes, or just saying yes? Do you understand this, Divya? Like whatever we have discussed till now, like let's say viscosity, that the first, from the beginning we have calculated viscosity. Let's say this one, this definition, it itself come with the strain rate, which is nothing but deforming. Also this strain, this is also deforming. So this thing, both elasticity and viscosity, comes from the basic fundamental question of how the material responds with an external deformation. Fine.
Yes, sir.
Okay, now in this context only, how do you differentiate between elasticity and viscosity? So I'll tell you as a line, you tell me it is makes sense or not. So elasticity tells you how the material, how much energy the material has stored upon deformation, and viscosity tells you how much it has lost upon deformation. It doesn't make sense, right?
I didn't get that, sir.
You didn't get it. Yes, definitely. I didn't say it properly. So let's say you have a material that looks like this. That looks like this. Okay. Now you deform it. Let's say you made it like this. Okay. Hmm? So you have, from this thing you have sheared it. This is shearing, right? This you know. This shearing. Let's say if it was an elastic material, what will happen? And if it was a viscous material, viscous fluid, elastic solid, what will happen? Let's say you deform it. What happens with viscous fluid? Let's say what happens with fluid if you deform it?
So what its configuration changes or shape changes?
Exactly, its shape changes, and the new shape obtained, is it a permanent shape or is it a temporary shape? Like let's
If
say
it is
you
elastic, it means it comes back to
comes back. Yes, does not come back. So whenever you have deformed it, let's say this was in molecular level, this was their molecular structure. Okay, this is the distance. Now the moment you have deformed it, let's say this layer has gone here, this layer has gone here, and this layer haven't moved, right? Let's say this. Okay, so this bond length you see earlier, carefully listen, it will be interesting. So let's say these two, so this has gone here, this has gone here, right? Now let's say this one, this length and this length, which one is higher, one or two?
Second one.
Second one. So what I'm trying to say here is these two atoms were the previous position, these two are the new position, right? Now if the distance has increased between these two, the energy will also increase, right? Because let's say you have, you know, Leonard Jones like system. Do you know Leonard Jones potential?
No, sir.
Okay, so this, you might know, sigma by r to the power 6 by r to the power 12, this kind of, anything rings a bell? No? Fine, no problem, I'll tell you what. So this stored energy of a material can be expressed in terms of the distance between two atoms. This you know or not? This you agree or not? What is the energy of the system? No, right? Okay, forget about it, I will not go in this direction, it might be confusing for you. So just let's stick to this comes back and does not come back. Let's say you have, do you remember this curve, stress strain relationship, this?
Yes, sir. Yes.
Yes, so this is called the yield point. After this it does not, like if you remove the strain here, it comes back. If you remove the stress, the strain comes back, but if you remove it here, it comes back. There is a finite deformation, right? Rings a bell? Divya?
Sir, the question?
No, there is no question. Does this ring a bell? Like, does you remember anything about this? Reading about?
Yeah, it was 12th standard.
Exactly. So, what does this finite deformation means? It means the distance between two atoms has changed. That's why it has stretched, right?
Yes, sir.
Makes sense or not? Like, by your physical intuition, whatever you know about this world, if
It won't be elastic anymore. Like it won't comes back to.
it wouldn't
It
come,
won't regain its original.
it would not regain its original shape. But this, exactly this finite deformation happens for fluid all the time, right? You only said does not come back and just comes back.
Fluid is different than solid also. I mean,
Exactly,
at that time.
that's what I'm trying to say. Fluid does not regain its original shape if you remove the deformation, but solid does. So something, there is something that solid is storing, that is the fluid is not storing. This something is called the elastic stress. So this coming back to its original shape, let's say you have deformed till this point, this coming back is a very fundamental thing that differentiate a fluid and a solid. Oh, sorry, yeah, fluid and a solid, correct?
Yes, sir.
Yes. So when you are deforming it, the solid is storing the energy change. Like if you deform it, if you put pressure on something, it will store the energy, and the moment you release your deformation, it will release the energy and come back to the original original state. Okay, but if you have a fluid, it does not store the energy. The moment you deform it, it it releases the energy and relaxes to a new state. Does it make
Yes,
sense or not?
it happens so.
It happens like in terms of this kind of storing energy or not, this in this scenario. Makes sense. So solids stores in deformation, liquid loses in deformation. These lines, can I write these two sentences?
Yes.
Okay, so if we have some measurement of how much a material is storing and how much material is losing, we can have tell that what is the how much of that material is solid like and how much of that material is liquid like.
Yes, sir.
Fine. There comes this concept of oscillatory shear. This is very important. Like if you stay in this area, you might come across this oscillatory strain. So oscillatory strain is you take a material and you vibrate it, like like once you do this and next time you do this, like let me, so this is the original, this was previous. Okay, so your strain epsilon is, let's say, sine omega t. Omega is your omega 0, let's say, frequency. Any problem here till this point?
No.
You understand this? What do I mean by epsilon 0 sine omega t? Hmm?
Yes, sir.
Yes, or like
Sir, I have a doubt
okay.
about the shear thinning and shear thickening. Can I send the mail or can I ask now?
No, you can ask now, or you can send a mail, whatever you like. You can ask now.
Mm.
Here.
They gave for the shear thinning and shear thickening. I've looked
Hmm.
net also.
Hmm, hmm, hmm.
Uh, the graph was the one that looks like log x graph will be shear thinning, and one that looks like parabolic will be shear thickening. Yeah, they provided so, but it will be above and below the Newtonian fluids graph.
I don't understand what you're saying. Okay, let me tell. Do you say? Are you saying something like?
Log x graph you have drawn. Like, for shear thinning, you draw a graph.
Hold on. Are you saying this kind of graph?
No, no, no. Um,
This graph.
Shear thinning graph.
This
That will
one.
be placed on the top of. Is it a problem? Like placing that
Oh,
graph.
you are saying this.
Uh,
No, no, no.
yeah.
It's not a problem. It's not a problem. So if you extend it, it has to cross it, right? Like let's say
Yeah.
I draw this like this. So this.
That won't be a. The values will be changing accordingly. So
No, no. Let's say, okay. let's say you have dot sigma, this is your Newtonian, right? And you are saying
Mm.
this
And below
and this.
parabolic graph.
Okay, let's say I extend this and this. What does it make it?
Same as the.
Same, yeah, it's same. So this region, like it just depends on these values. It can be anything. Okay, thank you for pointing. I should have done it like this. That is, this is a better way of representing. Fine, yeah. Yeah, this doesn't make any change of the argument that if you uh, epsilon dot is very high, it will behave more like a thinner, mm, more like less viscous fluid. Let's say it like this. So if you look at internet, you can find this plot also. This is epsilon dot versus viscosity. So for elasticity, this one, it's like this. So this is Newtonian, this is shear thinning, this is shear thickening. You can find a graph like this also. Probably these are log scale. Fine, or still not convinced. Which one?
Yeah, I got the first one that was I doubt.
Yeah, it's fine, right? Or still.
Yeah, it's clear, sir. It's
Okay.
clear.
So I was here in the oscillatory shear. Okay. So this you understand, right? So I am shearing it in a periodic manner, and I am calculating its stress. Okay. So in a linear region where stress, linear region means this region. So stress will follow strain, right? Like let's say this is my strain versus time graph, epsilon t versus t. Okay. So what will be the stress? So here it should follow, then it comes back like this. Sorry, this is like, yeah, you understand what I'm trying to do. This is our sigma t. Any doubt here?
No, sir.
No. So epsilon also, sigma will also have this similar profile with, let's say, sigma 0 sine omega t. Now if it has some fluid and solid behavior both, then this sigma will not exactly follow the input strain. It will have a phase lag. This lag, phase lag. Fine. So if the material is viscoelastic, it will have a phase lag. It would not exactly follow the input strain. It will relax in between. Fine. Now this phase lag value will give you this. So this is also stress by strain. This is like a Young's modulus, but it in a different context. So sigma 0 by epsilon 0 cos delta, and g double prime is sigma 0 by epsilon 0 sine delta. So this is called storage modulus, and this is called loss modulus. Now Divya, tell me, what if this material is perfectly solid? What will happen to this graph? Any idea?
Show the equation.
Equation is no. Just tell me in the from the physics intuition. So it's perfectly solid. You are in the linear region, so there is no permanent deformation happening. Now you are deforming the material with some epsilon. What will be the sigma? Will there be any phase lag here? This, will there be any lag, or
No.
the material will exactly follow the input? Which one?
For fluids, there will be a phase lag. No, for solids, there will be a phase lag.
Why the for solids there will be a phase lag? Phase lag happens.
After
So let's say, okay, see.
after some point, like in the previous graph you showed, deformity happens after
No, no, we are
time.
no, no, we are in between here. We don't cross it. Let's say it's happening like this. Way behind, like very small region.
Then there won't be a phase lag.
Then there will be a phase lag for perfectly solid, right? So if delta is 0, what happens to G prime and G double prime?
G double prime becomes 0
0.
and Z prime becomes maximum.
Correct. And if delta is pi by 2, then G prime is
Opposite.
0, G double prime is sine delta. So pi by 2 means exactly opposite phase.
Yes.
Shit. So what did you learn from this? Now let's say if you had a viscoelastic material, you do this experiment, oscillatory shear, and exactly by this phase lag, sorry, you can tell how much the material is solid like from the G prime, this is solid like, and how much this material is fluid like from the G double prime. Fine. So this is a very good measurement of viscoelasticity, and you will come across, if you stay in this kind of rheology related stuff, you will come across this concept a lot. Okay.
Okay, sir.
So any doubt or any confusion here? You can ask later also. Just take your time to grasp it. Maybe it can feel a little bit heavy right now, but you will understand eventually. Properly understand. Don't worry. Fine.
Okay, sir.
Okay. So do one thing. Definitely send those two assignments here. Okay. Do you need to note it down or something, Divya?
Sir, if I have doubts regarding the project work and all, which email should I contact
You
you?
can contact me in this email. Project work means which project work?
My fourth semester, we need to do a project, so I have some doubts regarding.
Okay. I thought there is a project related to this course only. Okay, yeah, you can do that. Fine. So send me the assignments, and the another person who was here try to join Tuesday also, Kanumuri, and I hope the other people will eventually join the class. So next day what I will do is I'll discuss. What do I write it? What the hell? Okay, so next week I'll do discuss week 1 assignment, and week 2 assignment I would not solve the exact questions what are there. I'll try to give hints, or yeah, like from the hints, or we can try to solve it together on that day. Okay, will this be fine by you? Okay, so good. Okay then, I hope you liked the class, or what how was it? Like, you'll anyway give feedback, I'll know from there. Okay. Right, Divya?
Yes, sir. It was beneficial for me.
Okay, you are, because you are a physicist, you understood things very easily. I am also a physicist, so I try to keep it not physics, or like I don't take for granted. I try to make it more for the other students. But anyway, let's see how the crowd goes. If now no one shows up, we can have this kind of discussions if you want. Fine. So okay then, send me the email. I'll see you. Okay.
Sir, I should send the week assignment questions to you, right?
Just questions, yeah, questions. Yeah.
Okay.
Okay.
Thank you, sir.
Thank you. Bye.